Hi, and welcome to week 5 of Science 137, Introduction to Meteorology at the American Military University. Hope you're doing well, and hope you did well on your first quiz, which was last week. Actually, the scores are pretty good. So this week is a light week assignment-wise. We first have a lab assignment on rain gauges, and a lot of great stuff. This is one of the med-ed assignments that people love or hate. Nolan Deskin is now the Colorado State climatologist, and he's done a lot of great work in increasing the number of people that are involved in observing rain and snow in the U.S. He's a phenomenal guy. So this module is a voiceover by Nolan. I think he's got still pictures. It's not as heavily produced as, say, the Antarctica one, but he'll make some good points about some things involved with taking rain and precipitation observations. So listen for how snow is affected when you're doing precip observations. Listen for the different types of rain gauges and kind of when they've been put into use and generally how they work. And some of the issues with observing rain. Do we tend to undercatch or overcatch rain? Does it matter where a rain gauge is located relative to buildings or woods or flat land and all of that? And all of these factors can come into play in the accuracy and the precision, more so the precision, of our rainfall measurement. All right, so besides the lab module, we'll go into the course content, which is a little bit about stability and instability, and we'll deal with that right now. And then I'm going to recycle some things about winter precip types that I recorded a few weeks back that I think actually turned out pretty well. I'm not going to try to redo it. So it'll be the same silly little process with the markers that we saw a few weeks ago. Have a great week. Some more explanatory content follows. As always, please send me a message if you need some help or some understanding on timing issues. And if you are on active duty, please stay safe, and thank you for your service. All right, so stability and instability is a topic that takes up about the first half of the chapter, and it's an important topic that we'll circle back on when we talk about severe weather, or thunderstorms and tornadoes in week 10. So just before we jump into the meteorology of stable versus unstable, first think about just your life. And if you know a stable person, if you poke or prod or perturb or disturb that person, push him off center a little bit, a stable person may react to that change, but they will come back to the person that they were before that change. Your long-term relationship with them, not going to change. They're not going to change as a person. They're just going to be perturbed for a little bit and come back. An unstable person may react to a small nudge in a huge way, much bigger than the original nudge. They may change as a person. They may change their relationship with you. They may go off and do things that are much bigger than the original disturbance. That's an unstable person. Taking those concepts to meteorology, it's talking about the same thing conceptually, but we're pretty much talking about whether thunderstorms are going to be born or not. In a stable environment, and we'll get into the kind of relative math in a second, but in a stable environment, if you lift a piece of surface air, it's going to go up, and once the lifting is done, it's going to come back down, and nothing big is going to happen. In an unstable atmosphere, in an unstable environment, if you lift a piece of air, a parcel is what we call this, it's going to go up, and if the environment is unstable, it's going to accelerate upward. And that is the beginnings of an updraft or a thunderstorm. So stable, what goes up comes down in proportion to the disturbance. Unstable, a nudge of a small amount can lead to a violent thunderstorm. It could multiply many times over and accelerate and get really big. All right, so that's the conceptual stability versus instability as well. So What is stable versus unstable? Okay, first of all, regardless of stability or instability, the atmosphere cools as you go up. So as you go up in the atmosphere, it's going to cool by a certain amount for every 1,000 feet that you go up, and that's called the lapse rate. The lapse rate is a measure of how rapidly the atmosphere cools as you go up, and it's not the same all the time. In a stable environment, that atmosphere cools less dramatically as you go up. In an unstable environment, that atmosphere cools rapidly as you go up. And the reason that lends itself to stability versus instability is going back to our parcel from the surface. If you lift a parcel, it's going to cool off as it goes up and the pressure drops, and there's stuff in the chapter about the pressure temperature properties. But just know, if you lift a parcel from the surface, depending on its moisture content and its original temperature, it's going to cool off in a prescribed way as it goes up into the lower pressures of the atmosphere. If the atmosphere around that parcel as it goes up is stable, it doesn't cool as dramatically with height, which means after that parcel is lifted, because the rest of the atmosphere doesn't cool very dramatically with height, it's going to find itself in a situation where it is cooler than the environment around it. The environment around it is relatively warm, it's going to be cooler and therefore heavier or more dense, and it's going to come back down. That's a stable configuration. Disturb the parcel, it finds itself heavier than the air around it, it comes back down. And that's what happened when the atmospheric profile, the background atmosphere, doesn't cool dramatically as you go up. In an unstable environment, the atmosphere cools rapidly as you go up, so that the air aloft is very cold relative to the parcel that's getting lifted. So in an unstable environment, some process will lift a parcel, which is like a front or anything that can nudge air upward, and that parcel is going to rise and cool, but the atmosphere around it is going to cool even faster than it has cooled. And so it's going to find itself in a situation where it's warmer than the air around it. It's like a hot air balloon. And hot air balloons rise because they're warmer than the air around it and less dense. And so it is going to accelerate upward. So it's going to take that initial nudge upward and accelerate even faster because the air around it is cold and dense and it is relatively warm and light. And that is the cartoon version of stability versus instability. So the final word on stability and instability is, again, to beat a dead horse, deader. Stable atmosphere doesn't cool very dramatically with height. It has a lapse rate that is a smaller number, less cooling with height than an unstable atmosphere, which has a large number, much cooling with height. And then in between those is a concept called a conditionally unstable atmosphere, where the lapse rate is between that of a stable atmosphere and an unstable atmosphere. Make sure you check out the numbers in the book, and also know that the types of clouds that you see have a lot to do with the stability class. In a stable environment, you still have lifting, so you will still have lifting of moist air that can create clouds. It's just that lifting doesn't cause additional vertical growth. So the clouds that you see in a stable environment would be kind of the flat, gray, stratus, layery type clouds. The clouds that you'd see in an unstable environment have vertical growth, cumulus clouds, thunderstorms, even layers of clouds in the middle of the atmosphere that have some vertical growth, that kind of popcorn, cauliflower, cotton ball look, where you have some vertical growth going on in there. Those are associated with an unstable environment. We'll go over some winter scenarios. You'll see this play out a lot. Almost everywhere, almost every day somewhere in the United States is dealing with rain and snow, and there'll be the band of mixed precipitation, and you'll always, if you wonder why do we go from green to this pink band to snow, here's kind of what's going on. So my son has 1 million Sharpies, and we're finally going to put those to use. So this is a hypothetical of the atmosphere. Okay, so we're going to go over 4 precipitation types: snow, freezing rain, actually snow, sleet, freezing rain, and then rain. These are the 4 major precipitation types that can occur during the winter. So what we have here is just a schematic. So this is the ground, and as we go up in the atmosphere, we're going to measure the temperature. And each one of these diagrams is going to go from left, it's going to be cold, to right is going to be warm, and we're going to draw a temperature trace on here as we go up. So everywhere to the left of this dotted line is going to be below freezing. Everything to the right of the dotted line is going to be above freezing, or warm. So warm in this context just means above freezing, warm enough to melt snowflakes. And so what happens is I'm going to draw, say, the temperature of the atmosphere going up, and in this scenario we'll keep the whole temperature trace, the whole temperature profile on the cold side of this freezing line. And what that means is snow or precipitation that generally starts up higher in the atmosphere as snowflakes falls through an atmosphere that is below freezing all the way from the precipitation origin to the ground, and so at no time will this atmosphere melt the snow. And so when the atmosphere looks like this from the ground up, as long as that temperature trace stays on the cold side of the freezing line, it's going to produce snow. So snow is this is what a snow sounding would look like. All right, another scenario is, I'll trade, we'd not be able to do it that way. So another scenario would be, what happens if the atmosphere, all precipitation in the winter is generally going to start out as snow on the left side of this dotted line. What if it has a little warm nose and then a deeper, relatively deep and cold freezing layer at the surface? So what's going to happen in this scenario on the right here is we start out as snow below the freezing line or left of the freezing line in cold temperatures. So precipitation is going to fall as snow, and then it's going to encounter this little warm nose. It actually looks like a nose, and that's the melting layer or warm nose, and that's where snowflakes are melted. So once it falls through a piece of the atmosphere that is warmer than freezing, that snow not immediately, but very quickly melts, and we become raindrops or droplets in this scenario. But then it goes through a fairly deep and fairly cold layer near the surface, so it will refreeze before it hits the ground. And that is what produces ice pellets. So if you're in a winter weather situation and you get that pelleted icy kind of sleet is exactly what it is. So this is a sleet sounding. And again, the difference between a snow sounding and a sleet sounding is a snow is on the cold side of the freezing line. It's always below freezing from the precip origin down to the surface. In a sleet scenario, we are cold and we have a melting layer, but then we have several hundreds of feet and very cold temperatures to help refreeze those drops that melted here. So down at the ground we would experience frozen precipitation. All right, this is very low tech. Another situation similar to sleet. In fact, it is one of the toughest forecasts in the business, is determining precip type between snow, sleet, freezing rain, and etc. Is, let's say we, again, in the winter, it is very much below freezing, high in the atmosphere at the origin of the precipitation, and we have a melting layer, and then we have a very small freezing layer or refreezing layer. So what happens in this scenario, much like the sleet scenario, the precipitation starts as snow. It falls through an atmosphere that has a warm nose, and that snow melts. It turns into droplets. Those droplets warm to whatever temperature they're falling through, or at least close. And then there's this very shallow sub-freezing layer near the surface. And what happens here is, even though the snowflakes melt in the melting layer, they don't have the time to refreeze before they start hitting objects on the ground. So they're actually very, very cold water when they strike the surface. Now everything that's down here, like people and power lines and trees and anything elevated off the surface of the earth, is going to be below freezing. So when those water droplets hit trees and power lines, it's going to refreeze at the surface and cause a glaze of ice. And if there's a lot of precipitation, it'll cause a giant, coating and caking of ice. So this is a freezing rain scenario. And freezing rain is different than sleet in that sleet drops and strikes the surface as a pellet and typically pretty harmlessly bounces off stuff. Freezing rain strikes the surface as a liquid and then almost immediately freezes. And it can accumulate on trees and on power lines, and these can be catastrophic storms in the winter. The energy industry, the electrical transmission and distribution networks can really get hammered by these things. It can cause billions of dollars of damage in just the electrical infrastructure. And the ecosystems can get hurt by freezing rain as well too. You bring a lot of tree limbs down, that's a shock to the system for the natural systems. And then of course, if you're walking around in this stuff, you can slip and fall, a lot of injuries, a lot of traffic accidents. So this is a nasty scenario. So this is freezing rain, and that is usually where you don't want to be. That's probably the least desirable scenario that you want. Finally, let's say you have a temperature profile where you start out as snow and you gradually warm as you get to the surface and you stay above freezing at the surface. Well, the snow melts, and even though it's winter, you're above freezing and you get very cold rain, which is in the south. This is the most common type of winter precipitation. Those of us who live in the south, we see rain more often than we see the frozen stuff in the winter, because we don't spend a whole heck of a lot of time below freezing or for any length of time. So these are the different scenarios. Again, we'll flip through them and apologize for the low-tech approach. But the warmest scenario is rain. That's liquid at the surface, and it stays liquid. It doesn't freeze to anything. It runs off just like a normal summer rain. The second warmest scenario is freezing rain. You have a warm nose and a very shallow refreezing layer. In fact, it's not a refreezing layer because the droplets don't have time to refreeze. They refreeze once they strike something, stick to it, and then coat it, causing all of those problems. The next scenario is sleet. It looks a lot like freezing rain when you look at the temperature profile, except that this refreezing layer is deeper and colder. And so the droplets that fall through here have the time and the temperature to refreeze before they hit the ground. And then the coldest scenario is snow. When you have snowflakes hitting the ground, that means that the temperature was below freezing from the point that they became precipitation all the way to the ground. So if you want to arrange these scenarios from cold to warm, snow's the coldest, then sleet, then freezing rain, and then rain itself. And those are the winter weather precipitation types.